Hello again, everybody. It is time for the last video in lecture module 1. We have now built all the protoplanets. We understand how the terrestrial planets were built, the gas giant planets were built. We understand that we have a Kuiper Belt made out of small, rocky, icy objects. What is left? Well, we left the story just after we formed everything, and now we have to clean up and take our solar system, our newly formed solar system, still full of a lot of leftover stuff, and transition it to the modern solar system we see today. We have to do post-planet formation modification. Our last bit of the story, and it is going to explain our last pieces of evidence of why we have such a solar system that is devoid of material other than the planets themselves, left in isolation. And it's going to explain the late heavy bombardment and why there really is, if we look at it in detail, less material than we expect in the asteroid belt and in the Kuiper Belt. In the process, we are going to form the Oort Cloud as well. Here we have to use our lessons from extrasolar planets that we learned about and apply it to our solar system. So let's get started with the last bit of material for Module 1. And we will have formed our solar system. So post-planet formation modification. What are we going to do first? We're going to clean up. Formation is a messy process, and we've left behind a mess. We still have nebular gas and dust to get rid of. Cleaning up the gas and dust is pretty easy. We just need to take the proto-sun and make it the sun. No biggie, just turn a star on, right? And then we're going to have this disk of planetesimals and protoplanets that need to be cleaned up, leaving us with our 8 planets, or 8 protoplanets: proto-Earth, proto-Mars, proto-Jupiter, so on and so forth. So we just need to clean up a bit. The major process that's going to be cleaning up the protoplanet part, once we get rid of the gas and the dust, is going to be planetary migration, mostly of the giant planets, both the gas giants and the ice giants. This is going to remove a lot of material from the asteroid belt and the Kuiper Belt, stir things up a little bit, and in that stirring up, as Jupiter and Saturn are migrating around, and Uranus and Neptune are doing that as well, we're going to create the late heavy bombardment. We're going to pummel pretty much every object in the solar system as we sling around all the leftover planetesimals and protoplanets. And the net result is we will end up with the Oort Cloud in the current state of the solar system. How do we get there? Well, let's go ahead and pick up. Let me make our screen full. There we are. And we're off. So, the 2 things that we need to do is clean up the gas and the dust, and we have to remove the solids and the planetesimals. This is all after planet formation. So let's assume that we've already formed our gas giants, our terrestrial planets, our primordial asteroid belt, our primordial Kuiper Belt, and let's see how we can clean this up. We'll start by removing the gas. This also takes care of the dust. This is a fairly simple process. Our whole story so far, we have not talked a lot about the star of the solar system, the becoming sun, our proto-sun. As stars turn on, as the proto-sun becomes the sun, as proto-stars become stars, they go through a period where they have pretty violent and strong, what we call stellar winds. They are ejecting material. Mostly hydrogen nuclei, protons, are just streaming out throughout the solar system, all 360 degrees around the star, or really should say 4 pi radians around the star if I'm talking about 3D. So now we are going to have these strong solar winds. And actually, we should talk about the light itself. Light carries momentum. It could push dust particles. But mostly it's going to be the solar wind. As the sun is turning on, we're going to have these strong solar winds. And these winds are going to push against the remaining gas and dust, blowing a bubble in outer space that's going to sweep through all the region of the solar nebula where we built all of our planetesimals and protoplanets, and actually out beyond that. We can actually see that we live in a small bubble, devoid of material, that was blown out by our sun currently. There's a region like this around all the stars. So the solar wind blows away the remaining gas and dust, and what are we left with? We now have a disk of planetesimals and many protoplanets, much more than the 8 planets that we have now. Some will survive, some will not. And here we start the more nuanced part of it. So this is some pretty modern ideas. None of it is, well, I shouldn't say none of it. The general story is accepted, but some of the details are still up for debate. So I'm going to give you the general story, and I'll try to end with some of the nuances and the fine details, where a lot of my own research comes in, trying to suss out those details and figure out the specifics that happened in our solar system. But let's stick to the generalities, the things that we know that happened, and the general processes in which the events occurred. So we form our disk of protoplanets. This is after we get rid of the gas and the dust, and that's what this plot is showing. It's a rather complicated plot, but notice that you have a series of images. As you move down, you're going to later times after you have formed all the planetesimals and protoplanets. So at the beginning, we are looking at the red is showing us small little planetesimals made out of rock and metal, our prototerrestrials, our terrestrial planetesimals, and our terrestrial protoplanets. Then we have this lighter blue color where we have some hydrated material. So we have some organics, and we have some evidence of water ice as well. And notice this is where Jupiter, Saturn, Uranus, and Neptune, these are our initial starting locations. Up here is distance away from the sun in astronomical units. Here is where Earth currently is. This is where Saturn currently is. Notice that everything's a little bit more scrunched in at the beginning. Planets are going to move around a bit. And then the outer regions of our solar nebula, this is where we have all of our exotic ices. So we see that temperature gradient. So initially, our giant planets, particularly Jupiter and Saturn, are going to migrate inward towards the sun. This is a process that would make Jupiter a hot Jupiter unless something happens that saves the situation. Now, why would we expect inward migration? And this one can be understood if you go out in your car, get on the highway, start going down the road at about 60, 70 miles an hour, and then unroll your window and stick your hand out. What happens to your hand? You feel the wind blow it backward. The wind is pushing on your hand, blowing it backward. You feel what we'd call a gas drag blowing your hand backwards. Here we have at least the cores, if not the already formed gas giant planets, embedded in the solar nebula, which still has gas. So these gas giant planets are plowing through the nebular gas. They're feeling a wind that's pushing back on them, a gas drag. What this does is it sucks out their angular momentum, and they have to move inward as a result. So initially, gas drag makes Jupiter and Saturn migrate inward. Uranus and Neptune are still forming at this point. Jupiter and Saturn form the fastest and form first, and they migrate inward. As they are migrating inward, what's going to happen? Well, all the little planetesimals they run into, these smaller, lower mass things, much lower mass than these gas giants, they're going to get bullied about by Jupiter and Saturn's massive gravity. So they're going to start mixing up the material and slinging around all the leftover planetesimals. Here, you can see that the terrestrial planets are still being put together. They're still accreting in their own games of Highlanders. So you're starting to form some pretty big protoplanets that are going to become our proto-Mercury, Venus, Earth, and Mars. But notice now we're mixing up a little bit of the asteroid belt, where we're still going to have mostly S-types, and then we're going to transition to C-types, but we see some C-types in the inner parts and S-types in the outer parts. Those are details you don't need to remember, but I'm trying to do this story justice. So, initial inward migration. This inward migration of Jupiter is a natural process. This is how many planetary systems end up with their hot Jupiters. Something different must have happened in our solar system. Something must have halted Jupiter's migration to become a hot Jupiter. And the key to that one is Saturn, which formed slower and formed later. And this is a hotly debated idea, but Saturn forms later, and it starts to migrate inward until it's orbiting the sun once for every 2 times the Jupiter does. So every time the Jupiter comes back around, Saturn's giving it a tug saying, hey, come back this way, come back towards me. So this sort of a resonant behavior, as we call it, saves Jupiter, and then they migrate outward together, which is also just an expectation of once we get rid of all the gas and we start forming larger and larger planetesimals, we expect things to naturally migrate back outward. So what was inward migration is now outward migration. Why Jupiter didn't become a hot Jupiter? We think Saturn swung in and saved it. It would be an interesting thing to go ahead and look at all the extrasolar planetary systems out there, and the ones that have lots of planets with terrestrial planets to the inner parts and then gas giant planets. Are there two gas giant planets? Is this a common mechanism where you need a second gas giant planet to save the first one from becoming a hot Jupiter? And there's also the issue of timescales. Again, a little bit more detail, but this is a pretty fascinating story and I want to do it justice. So we had our initial inward migration stirring things up, and now we're going to have slow, steady outward migration. And this slow and steady outward migration, we need to consider what the gas giants are doing and what the ice giants are doing separately. So the gas giant planets, they're the most massive. They have stirred up, kind of destabilized all these protoplanets and planetesimals. They're just ready to get slung around. So as these planets migrate outward, Jupiter and Saturn, they are going to pretty much gravitationally throw out most of the material they encounter, the leftover planetesimals, directly out of the solar system. Bye-bye, you're not coming back. They're ejected at past the escape velocity for our sun. So they clean out all that material. Uranus and Neptune, being less massive, they're migrating outward too, and they're going to stir up and sling material around as well, but at lower speeds because they're lower mass and have less gravity. So the material that they sling around, a lot of it is going to end up being slung out to the outermost regions of the solar system, forming our Oort cloud. Also, removing a lot of the material that we expected from our Kuiper belt as they migrate outward and redistribute all that material. The net result of all of these giant planets moving around is these leftover small planetesimals and protoplanets are getting slung throughout the solar system in every which direction, creating a lot of potential impactors to impact objects like the moon and Mercury and everything else, including the sun, causing this period of the late heavy bombardment. So the late heavy bombardment is a result of this planetary migration, this redistributing and getting rid of most of the planetesimals. Some are slung out of the solar system entirely. Other ones impact other objects, become part of them, accrete onto them in this period of late heavy bombardment. And then we proceed with time. The planets are now mostly where they are going to end up, and we end up with our modern solar system down here at the bottom, where we have our terrestrial planets. We have an asteroid belt with mostly S-types in the middle, C-types in the outside. It's mixed up a good bit. And then we have Jupiter with its Trojan asteroids, Saturn, Uranus, Neptune, and here's our Kuiper belt. But a lot of material has been removed. So less material than we expect, and that's exactly what we observe. Over there is pretty much a summary of what's going on, of how we got our late heavy bombardment. If you're curious to look up details about these, now I have the specific models that are trying to describe this specific behavior. Take this general and make it a little bit more specific. So this initial inward migration where Saturn saves Jupiter from becoming a hot Jupiter is described by what's called the grand tack model. It's a sailing reference, like tack into the wind. You go an angle and then another angle into the wind. So inward, outward migration. You can look up the specifics if you want. You can type grand tack model and planetary formation, and that'll bring you to more information on it. The specifics are hotly debated, so I'll leave you at that. Talk to me in our Zoom Q&A or send me an email about that. This later point, where we have this outward migration causing the late heavy bombardment and leaving us with the planets as is, with our asteroid belt and our Kuiper belt, is called the Nice model. That is the city in France, Nice, which is where the meeting was, where this was originally put out into the world of planetary system formation. So, just a point that you should be aware of. If you are interested in this and you're going to look up the Nice model on Google, don't do what Dr. Lindsay did and just type in Nice model into Google search with your office door open and hit enter. Notice that Nice also spells nice. I'll let you go ahead and finish out the embarrassment that I suffered right after that. So add the word like solar system formation, planet, any of those things will make that a safe search for you. And that's it. That leads us to our modern solar system. We have all the planets in place. We have our leftovers, the asteroid belt, the Kuiper belt. We have created the Oort Cloud. We've created the Late Heavy Bombardment. We're left with a solar system that is disk-shaped. The planets all survive thanks to what appears to be Saturn. So we have nearly circular orbits for all the planets. And we have this nice gradient of terrestrial planets, gas giant planets, ice giant planets, Kuiper belt. I hope you really enjoyed this first module where I covered the entirety of solar system formation. This is longer than I expect most of them to be. Some of it was review material from when we were still having in-person classes, but attendance was dropping off, so I wanted to make sure that we covered it thoroughly. If you have any questions, of course, just let me know. Log on to the Q&A that we're going to be having on Wednesday and on Tuesday and Thursday as well for my other class. And I hope to hear some questions, and I will be posting the post-lecture engagement exercises shortly. Thank you for tuning in.